Thank you for choosing American Pest CEUs.
Hello everyone, Sean Reeves with American Pest CEUs. I'm an associate certified entomologist and I've been in the pest management industry since 1999.
This course was prepared by Jack Launius. Today's course is on aerial applications. Avoiding drift and off-target contamination in aerial applications. Let's look at some factors to consider. To avoid drift during aerial applications, several best practices can be implemented. 1. Droplet size control. Larger droplets are less prone to drift. 2. Environmental factors. Be mindful of wind speed and direction. 3. Application height. Lowering the height of pesticide release can minimize drift, especially in aerial applications. 4. Drift control additives. These can be used to reduce the potential for drift, but always follow label directions. Additionally, it's important to apply pesticides during calm weather conditions and avoid applying when rain is predicted for the next 24 hours to prevent wind or rain from blowing or washing the pesticide off the treatment area. Proper equipment maintenance and calibration are also crucial to ensure accurate application and minimize drift. Understanding pesticide movement. Pesticides can inadvertently move from their intended application site through air, water, and even via objects and organisms. This movement can occur indoors and outdoors, affecting air quality, water sources, and surrounding ecosystems. Airborne movement. Pesticides can drift away from the application site due to wind or air currents. This drift can happen in the form of spray droplets, vapors, dust, or even soil particles carrying the pesticide. Such movement poses risk to adjacent areas, potentially affecting sensitive crops, wildlife, and human health. Waterborne movement. Pesticides can also travel through water, either as runoff from the surface or by leaching through the soil. This movement can lead to contamination of surface water bodies and underground, posing significant environmental risk and health risk. Movement on objects and organisms. Pesticides can adhere to objects, plants, or animals moving to new locations as these carriers move. This can lead to unintended exposure in areas far from the original application site.
Strategies for reducing off-target exposure. Managing spray drift, droplet size control. Larger droplets are less prone to drift. Using appropriate nozzles and pressures can help create the desired droplet size. Environmental factors, wind speed and direction are critical. Spraying under calm conditions or when the wind is blowing away from sensitive areas can reduce drift. Application height. Lowering the height of pesticide release can minimize drift, especially in aerial applications. Here, Fairlift's unmanned aerial services drones offer a precise and controlled solution, ensuring optimal application height and significantly reducing the risk of drift. Drift control additives. These can be used to reduce the potential for drift, but always follow label directions. Temperature inversions. Temperature inversions can significantly increase the risk of pesticide drift. This stability can cause pesticide droplets to remain suspended in the air and travel considerable distances, potentially affecting areas far from the application site. Reducing waterborne movement. Point source pollution. This refers to contaminants that enter water bodies from identifiable, discrete locations, such as a specific spill or discharge point. Managing these sources involves careful handling of pesticides during mixing, loading, and disposal, as well as immediate containment and remediation of spills. Non-point source pollution, arising from general land areas rather than specific locations. It includes runoff from agricultural fields or urban landscapes where pesticides are used. To mitigate this, applicators should employ best management practices like maintaining buffer zones near water bodies and applying pesticides in weather conditions that minimize runoff potential. This should give you a good idea of pesticide movement and runoff. Avoid overapplication. This reduces the chances of runoff and leaching. Buffer zones. Establishing buffer zones near water bodies can prevent pesticides from entering these sensitive areas. Soil considerations. Understanding soil properties can help in choosing the right pesticide and application method to minimize leaching. Sensitive areas. Sensitive areas demand special consideration when applying pesticides.
These include proximity to water sources. Areas near surface water or with shallow groundwater are particularly vulnerable. Applicators should avoid direct application to water bodies and take precautions to prevent runoff and leaching. Institutions and habitats. Schools, playgrounds, hospitals, and habitats of endangered species require careful planning to avoid accidental exposure. Agricultural and residential vicinities, areas near apiaries, wildlife refuges, parks, ornamental gardens, and food crops are sensitive to pesticide drift and residue. Indoor environments, places where people live, work, or receive care, as well as areas where food is processed or stored, demand stringent control measures to prevent indoor air contamination. Environment. You must recognize how the following factors possibly influence the environment fate of pesticides: weather and other climatic conditions, types of terrain, soil, or other substrate, drainage patterns, presence of fish, wildlife, or other non-target organisms. Application safety. Aerial application safety processes and procedures involve the highly important components of the aircraft, the pesticide dispersal system installed on the aircraft, and ground equipment used to mix pesticides and load them into the aircraft. Each pesticide application you make is possibly unique for you because of differences between application site locations, obstacles, non-target areas, weather, pesticide materials, crops or target areas, and other variables. Therefore, you and the ground crew must begin by clearly understanding the work order and pesticide label. Arrange to scout the target site and surrounding areas so you can plan the application before scheduling it. Review the pesticide label to understand application restrictions and precautions and to prepare for emergencies or other problems. Some pesticide materials may have local application restrictions, such as time of use, height of application, prohibitions due to nearby sensitive crops, and requirements for buffer zones. Check with state or local pesticide regulatory agencies if you need information about additional restrictions. Overspray, drift, and other misapplication. As the applicator, you assume responsibility for any pesticide misapplication. Overspray, off-target movement, and other types of misapplication may damage surrounding crops, residential plantings, landscapes, and other property, as well as cause environmental contamination. These are all violations of pesticide labels, as well as many state pesticide control laws. Train ground crews to be alert during an application and quickly communicate with you if they spot any potential for such problems. Considerable financial liability and legal consequences may result from any damage caused by misapplication. Spray or dust containing bystanders or vehicles. It is illegal to apply any pesticide in a manner that exposes people, livestock, vehicles, or other objects to the spray or dust. Unfortunately, farm workers, joggers, trespassers, and others may not recognize the hazard of entering an area until an aircraft making an application flies over them. Weather patterns, especially wind direction, can also change rapidly, causing pesticide from the application to move off-site and possibly onto workers or other people nearby. For example, you might plan and begin an application based on the wind blowing away from nearby areas where people are present. However, during the application, the wind direction could change and blow towards these areas. Therefore, develop a plan that includes communication between you and the ground crew to delay or stop the application if anyone spots people nearby, and only make applications if no one is in adjacent areas where they might be subject to exposure. Inspect the application site and adjoining areas before beginning an application to confirm no one is around the site. In the emergency plan, include instructions to follow if spray contacts bystanders. This should involve decontamination methods and procedures for obtaining medical care for exposure victims. Off-target movement of pesticides is the condition where pesticides or pesticide residues leave the application site at any time and in any manner other than during a pesticide application. Often the physical and chemical characteristics of the pesticide contribute to or reduce the chances that the material may move off-site after an application. For example, pesticides that break down quickly after you have applied them will be less likely to move off the application site than pesticides that are highly persistent in the environment. Pesticides and pesticide residues can move off the application site in several ways after they are applied. These include post-application volatilization into the atmosphere of the pesticide that adhere to treated surfaces, the crop plants, the soil in between the plants or bare ground, Pesticides with high volatility are more likely to move off the application site than pesticides with low volatility. Leaching through the soil. At the application site and moving into surface or groundwater after application, pesticides with low solubility in water will not leach as much as those that are very soluble in water. Rainfall or irrigation water. Washing residues off the application site into surface waters after application, pesticides that have a high absorption potential are less likely to wash off plant surfaces. Blowing off the site. Attached to soil particles or dead plant material after application. Leaving the application site as residues on harvested crops. Being carried off the application site on vehicles, equipment, animals, and people. Being carried off the application site as fine droplets in an inversion cloud. During any application, a certain percentage of the spray droplets will drift. If the drift is confined to the treatment site so that it is part of the pesticide application, there is generally little hazard to the surrounding areas that are not part of the application. Pesticide drift, however, increases the hazard to people and other living organisms outside of the treatment site. The following information pertains to recognizing the causes of pesticide drift and ways to reduce this problem. Pesticide drift can cause economic loss. Drift of herbicides can injure some crops. Crops on nearby farms can become unsellable if the drifting pesticide is not registered for use on the crop. State and local agencies receive thousands of complaints about drifting pesticides each year and spend substantial resources investigating drift complaints. Factors that contribute to drift. The spray droplets and the percentage of droplets within a certain size range are the key factors affecting off-target drift. You can control some of these factors when making aerial applications. The unit of measure for the diameter of a spray droplet is a micron, also referred to as a micrometer. The mathematical symbol for a micron or micrometer is shown on the screen. 1 micron is 1/25,000th or 0.00003937 of an inch. To illustrate the relative size of 1 micron, the thickness of a single sheet of paper is about 100 microns thick. The longer a spray droplet remains airborne or suspended in the air, the greater the chance it will drift from the application site. A small spray droplet is more susceptible to drift than a larger droplet because the small droplet is lighter and therefore remains airborne much longer. For example, while it takes approximately 4 minutes for a 20 micron droplet to fall a vertical distance of 10 feet, it takes only 2 seconds for a 400 micron droplet to travel the same distance. There is a rapid decrease in the drift potential of droplets larger than about 200 microns. Conversely, research has proven that droplets smaller than 200 microns are very prone to drift. People who study drift classify droplets that are 150 to 200 microns or smaller as driftable fines. In wind speeds ranging from 1 to 9 miles per hour, droplets that are 200 microns or larger have an insignificant drift potential. For example, the theoretical distance that spray droplets move laterally while falling from 10 feet above the ground in air moving at 3 miles per hour would be only about 8 feet for 400 micron droplets. However, this distance increases to about 1,000 feet for 20 micron droplets. Higher velocity wind speeds increase the drift potential of all droplets. Droplets below 50 microns in diameter remain suspended in the air indefinitely or until they evaporate. Droplets of this size have no benefit to a pest control program other than certain vector control operations because they are never likely to reach target surfaces. Avoid using nozzles or nozzle orientations and configurations that produce droplets in this size range because there is no way to assure that these droplets will remain on or near the application site.
Classification of droplet size.
On this image, you're seeing an aerial spray droplet size chart. If we look on the left, we have the droplet size category. In the center, we have the droplet diameter or the microns, and we have the typical spray applications on the right. So when we look at droplet size category of ultrafine, we're going to be less than 50 microns. This is going to be a typical spray application of fungicides and herbicides. Our next droplet size category of very fine is going to be 50 to 100 microns, and the typical spray application is going to be insecticides, plant growth regulators. Next, we have fine droplet size category, 100 to 200 microns. These would typically be insecticides and fungicides. Our next category is going to be medium droplet size, 200 to 400 microns. These would be insecticides and fertilizers. Our next category of droplet size is going to be coarse. This would be 400 to 600 microns. These would typically be fertilizers, plant growth regulators. Our final category of droplet size is going to be very coarse. It's going to be greater than 600 microns. These would be fertilizers, agricultural oil applications. All nozzles produce a range of droplet sizes known as the droplet size spectrum. This means that even when you use a nozzle having a large orifice that mainly produces large droplets, some percentage of the droplets in the spray are going to be small enough to be prone to drift. A common classification method used to describe the droplet size spectrum produced by a nozzle is the volume medium diameter, or VMD. This means that half of the total spray volume of the nozzle consists of spray droplets smaller than the VMD numerical value, while the other half is larger than the VMD numerical value. For instance, a nozzle with a VMD of 400 micron sprays out half of its total volume in droplets having a diameter greater than 400 microns, and the other half in droplets having a diameter smaller than 400 microns. However, this does not tell you how much of the spray volume is made up of droplets that are smaller than 200 microns. With any spray application system, there is a range of droplet sizes created during the atomization process. This range is referred to as the spray droplet spectra and can be described in various ways. The volume medium diameter VMD, or DV 0.5 droplet diameter at 50% of the total spray volume is contained in droplets of lesser diameter, is commonly used. Another way of classifying the droplet sizes produced by a nozzle is to identify the percentage of total spray volume that contains droplets smaller or larger than a specific diameter, usually 200 microns. This directly addresses those droplets at risk for drift. For instance, a nozzle may produce 2% of its total spray volume in droplets smaller than 200 microns in diameter. This means that only a small portion of the droplets produced by this nozzle are at risk for drift. This type of description, however, tells us nothing about the size of the remaining droplets produced, which is the information you need to determine the type of coverage you can expect. The most useful way to describe the droplet sizes produced by a nozzle is to use droplet size categories based on the entire droplet size spectrum of a nozzle, rather than just the VMD or a specific size droplet by percentage of volume. The spray classification system is the American Society of Agricultural and Biological Engineers ASABE Standard S-572.1 Spray Nozzle Classification by Droplet Spectra. This classification system has 8 categories: extra fine, fine medium, coarse, very coarse, extra coarse, and ultra coarse. Using these categories, you can select a nozzle, orifice size, and operating pressure that produces the label recommended droplet size spectrum. All pesticide labels will eventually contain nozzle specifications and/or the required droplet size spectrum. Consult the pesticide label for specific instructions when selecting nozzles. Use the droplet size spectrum categories, determine which nozzle to use to reduce drift, and provide adequate coverage in a particular application operation. By selecting the appropriate category based on the type and use of a pesticide, you get acceptable results while keeping the risk of drift to a minimum. Nozzles. Nozzles provide the primary means of controlling 3 factors that affect any application and possible off-target movement of the pesticide: the application volume, droplet size, and spray pattern. It is important for nozzles to operate within the range of pressures and flow volumes prescribed by their manufacturers. Therefore, be sure that the spraying system is compatible with the specified pressure and flow volume ranges for the nozzles you use in the aircraft's speed. Manufacturers produce many types of nozzles for various liquid pesticide application situations. On the current slide, you're seeing different streams from a nozzle. At the top, we have a straight stream. Below is a flat fan. Next, we have an manifold deflection. After that, the hollow cone. Finally, the rotary atomizer. The application volume influences the type of nozzle used in an aerial application. Aerial application volumes fall into three categories: conventional, 5 to 15 or more gallons per acre; low volume, or LV, 0.5 to 5 gallons per acre; ultra low volume, ULV, less than half a gallon per acre. Traditionally, amounts less than 8 gallons per acre were the norm for conventional volume aerial applications. Pilots made these types of applications with cone pattern nozzles. However, aerial spray drift studies indicate that spray output from cone pattern nozzles are likely to emit drift-prone droplets until configured to produce coarser droplets. Many pilots now make conventional applications using straight stream nozzles, variable orifice flood nozzles, or flat fan nozzles. Application volumes in the low volume LV range are often suitable for certain situations, such as applying particular fungicides. You may use flat fan or variable orifice flood nozzles set to a suitable deflection angle based on orifice size, pressure, and aircraft speed for LV applications. Drift studies show that properly installed straight stream or variable orifice flood nozzles reduce the amount of small droplets that are prone to drift. When using vegetable oil carriers, or when you apply concentrates in forest or public health pest control, such as mosquito abatement spraying, ULV application volumes may be around 1 to a few ounces per acre. Rotary atomizers work well for ULV applications as well as LV applications. Straight stream nozzles. Straight stream nozzles oriented straight back often produce the largest droplets and the lowest drift compared to other nozzle types. These nozzles provide a way to produce large droplets at higher air speeds when you match the flow volume of the stream from the nozzle with the airspeed. However, at very high speeds, the large droplets produced by straight stream nozzles can shatter and create driftable fines. Fan pattern nozzles. Spray drift studies indicate that nozzles that emit fan-shaped spray patterns typically produce fewer, small, drift-prone spray droplets than do cone pattern nozzles. Flat fan and even flat fan nozzle tips produce flat, fan-shaped spray patterns. Flat fan patterns have the highest deposition in the center of the pattern, and deposition tapers off towards the edges. Even flat fan nozzle patterns are uniform across the whole width of the nozzle pattern. The exact angle of the fan-shaped pattern produced by these nozzle tips depends on nozzle design, spray pressure, and characteristics of the pesticide spray mix. Nozzle tips designated to produce fan-shaped patterns have angles of 25, 40, 65, 80, or 110 degrees. In general, fan nozzle tips that produce wide angles generate more drift-prone spray droplets. For this reason, fan nozzle tips designed to emit no more than 80-degree spray pattern are better suited for aerial spray applications. Typically, 40-degree flat fans are recommended for the higher speeds associated with fixed-wing aircraft, and 80-degree flat fans are recommended for slower speeds associated with rotary wing aircraft. Compared to standard flat fan nozzles, even flat fan nozzles have little effect on the spray distribution applied by an aircraft. The more critical consideration when using flat fan nozzles on an aerial boom is that the nozzle tip produces a narrow spray angle. Variable flow rate flat fan nozzles. Typically, nozzle orifice sizes are fixed, and the only way to increase or decrease nozzle flow volume and maintain a desired spray droplet size range at a certain spray pressure is to change the size of the nozzle orifice. With standard nozzles, slightly increasing or decreasing the spray pressure allows minor adjustments in the nozzle flow volume, but this adversely affects the optimum spray pattern. Variable flow rate nozzles overcome this problem because the nozzle orifice size is flexible and enlarges or gets smaller as the system pressure increases or decreases. This maintains greater integrity of the droplet size spectrum and spray pattern as system pressure changes. The advantages of variable flow rate nozzles include the ability to change application volume on the fly by increasing or decreasing system pressure instead of replacing nozzle orifices, better spray droplet uniformity that is less affected by system pressure changes. A more uniform application volume and spray pattern even when the application airspeed varies. Variable orifice flood nozzles. A variable orifice flood nozzle disperses liquid in a flood type, wide angle, flat, fan pattern, or a straight stream. The nozzle body has two manual adjustments, one for orifice size and the other for deflection angle. 4 orifices can be selected, plus an off position. The orifice size and pressure determine the nozzle flow volume. Spray from the selected orifice hits an adjustable deflector that you adjust to produce fine, medium, or coarse spray droplets. There are 2 common types of variable orifice flood nozzles. One has deflection angles of 30, 55, and 90 degrees, and the other has a straight stream setting and deflection angles of 5 and 30 degrees. Slower aircraft typically require larger deflection angles than faster aircraft. Rotary atomizers. A rotary atomizer consists of a screen mesh cylinder that rotates around the nozzle orifice. Its own fan or an electric or hydraulic motor powers this rotating cylinder. The higher airspeed of fixed-wing aircraft favors the use of fan-driven rotary atomizers. Most fan drive units have adjustable fan blade pitch so you can achieve the optimum cylinder rotation relative to the aircraft speed. The slower speeds of rotary wing aircraft require motor-driven cylinders. Spray droplets that emerge from the screen mesh cylinder are relatively uniform in size. Rotary atomizer nozzles deliver a wide range of application volumes. Because they have relatively large metering orifices, their nozzles do not clog as easily as conventional nozzles when applying low-volume sprays containing a high concentration of chemicals in suspension. Uniformity also depends on droplet size and nozzle spacing. The number of nozzles you need is based on how wide a swath you intend to cover. Typically, a single rotary atomizer can generate a swath of 10 to 15 feet. Hollow cone pattern nozzles. Hollow cone pattern nozzles include the disc core type and the whirl chamber type. Recent spray drift research indicates that using hollow cone nozzles on an aerial spray boom yields a disproportionate amount of very fine, drift-prone droplets. Because cone nozzles emit spray in a conical pattern, the effect of wind shear is greater than its effect on straight stream or flat fan spray nozzles. The orifice of a hollow cone nozzle is located in a disc that fits into the nozzle body. Discs are available in various orifice sizes to accommodate application needs. Located behind the disc is a core or spinner plate that puts a high rotational spin on the liquid passing through the orifice. The size of the disc core combination determines the gallons per minute (GPM) rating of the nozzle at a given pressure. A whirl chamber nozzle consists of a specialized nozzle body and nozzle cap. When liquid enters the nozzle body, the interior structure causes the liquid to whirl rapidly before exiting as a cone-shaped spray pattern. Whirl chamber nozzles are relatively free from clogging problems. Nozzle anti-drip devices. Equip all the nozzles on the spray boom with check valves to prevent dripping when you shut the spray off. These valves have spring-loaded diaphragms, needles, or steel balls that stop the nozzle flow when spray pressure drops below a certain preset amount, usually about 7 psi. Use anti-drip check valves in combination with shut-off valves that have the suckback feature. In systems where suckback is unavailable, use a stronger spring so the nozzles seal shut when pressure drops to about 15 psi. Spray mixture physical properties. 3 key physical properties of a spray mixture have a significant effect on droplet size in aerial applications. Dynamic surface tension. Surface tension is the force that keeps a droplet together. When the fluid that makes up the droplet contains adjuvants or other substances, the normal surface tension changes, but it takes a certain amount of time for the molecules in the adjuvants to move to the surface of the droplets. Therefore, the surface tension of spray droplets can change after the droplets are formed, causing a larger droplet to split into smaller droplets. Extensional viscosity. When the pump forces spray liquid through a nozzle orifice, it stretches to a certain point before breaking off to form a droplet. The amount of stretching or stringiness is the extensional viscosity. Pressure in the system, which regulates the ejection speed of the liquid, affects the extensional viscosity. Higher pressure lowers this viscosity, therefore producing smaller droplets. Shear viscosity is a liquid's resistance to flow. Some liquids are thicker and therefore resist flow or flow more slowly than less thick, or less viscous liquids. Spray drift control adjuvants, when added to the spray mixture, may help reduce the number of driftable droplets under certain conditions. However, reports indicate that some types of drift control agents lose their effectiveness when circulated through a sprayer pump. Studies show that some materials sold as drift control adjuvants actually do not perform as such. Spray drift control adjuvants are a specific class of chemical adjuvants, so do not confuse these with other adjuvants such as surfactants, wetting agents, spreaders, and stickers. These other adjuvants, and formulations containing alcohol or certain water-miscible solvents, tend to reduce the dynamic surface tension of spray droplets, resulting in smaller droplet sizes. The active ingredient ensures biological activity, and additives or adjuvants are compounds that are not biologically active and that are combined with the active ingredient as part of the formulation to help improve the performance of the active ingredient or modify the physical properties of the spray.
These effects cause changes in the spray formation mechanism, and breakup is altered subsequently. Droplet formation and size distribution may be significantly modified. These adjuvants or additives can be very diverse, with classifications such as water conditioning agents, surfactants, oil concentrates, humectants, evaporation retardants, ammonium fertilizer solutions, compatibility agents, defoamers, antifoamers, stickers, and drift suppressing agents, deposition and detention aids. External factors affecting droplet size and drift. Certain factors remain beyond your control. These external factors include weather such as humidity, rain, extremely high or low temperatures, wind, or conditions leading to an inversion layer.
Once exposed to the atmosphere, individual spray droplets will generally begin to evaporate. Evaporation removes water or other carriers, making the spray droplet smaller than it was when it left the nozzle. As the droplet becomes smaller, it becomes more prone to drift. Conditions that contribute to evaporation include air temperature. Evaporation is more rapid as temperature increases. Humidity. Evaporation is more rapid as humidity decreases. Air movement. Evaporation is more rapid as air movement increases. Distance from discharge to the target. The further the droplet has to fall, the more time is available for evaporation. Spray carrier. Water will evaporate faster than oil carriers.
The optimum time to make an aerial application when evaporation of spray droplets is a concern is during the coolest part of the day. Early morning is usually ideal because it is generally more humid at this time and wind speeds are often low. However, temperature inversion conditions may be greater during early mornings. Avoid making applications during hot, dry periods of the day. Keep the application height between 8 and 12 feet from the target to shorten the distance that spray droplets must fall. To minimize the risk of drift caused by evaporation, small spray droplets require lower application heights. Co-distillation. Pesticides can also move off-site through a process called co-distillation. This phenomenon occurs when the pesticide contacts very hot surfaces, usually soil with no vegetation. Pesticides, even those that are not highly volatile, leave the soil surface with water molecules during rapid evaporation that occurs immediately after irrigation. Fog also is available to pick up pesticides from the application site and carry them off-site. Effect of wind and thermal drifts and off-target movement. Air movement from wind or thermals is a major contributing factor to off-target pesticide drift. Wind carries lighter and smaller droplets away from the target site, where they accumulate until they saturate a given volume of air with the pesticide. As winds become stronger, the air traps more and more large droplets and may move them away from the target before they return to the ground. Upward air movement caused by thermals also entraps and moves small droplets, increasing the probability that they will drift away from the application site. Thermals occur as the ground heats up, usually in the afternoon, and especially after cool night temperatures. This causes air near the ground to rise. Since warm air is lighter, molecules are farther apart than cool air. Thermals occur as the ground heats up, usually in the afternoon, and especially after cool night temperatures. This is what you're seeing in the image above. This causes air near the ground to rise. Since warm air is lighter, molecules are further apart than cool air is, once again shown in the image above. Aerial herbicide application provides an efficient way to treat large areas of rangeland, pasture, and non-crop areas. However, if not done correctly, the potential for damage to nearby desirable plants can be significant. For land managers seeking to use aerial application for weed control, the combination of application best practices and new, non-volatile herbicides can offer a safer way forward. Physical drift versus vapor drift. Physical drift and vapor drift both need to be considered when planning for arable herbicide application. Although often conflated, the two are distinct issues. Vapor drift refers to volatility, which is the ability of herbicides to vaporize and transform from liquid to a gas, increasing the potential for off-target movement. This is a common problem with ester-based herbicides, which are formed with an alcohol, making it easier for absorption through plant leaves. Physical drift refers to the airborne movement of herbicides in a non-gaseous form from the target location into adjacent areas. Off-target movement can occur in vapor, droplets, mist, aerosols, dust, or other types of fine spray particles. In the current image, you're seeing some examples of what physical and vapor drift looks like. We'll give you a few seconds to review these images. Temperature inversions. Differing air temperatures and stratified layers of the atmosphere are responsible for the inversion phenomenon that can exacerbate the problem of off-target pesticide drift. Inversions occur when an upper layer of air is warmer than the air below it. The warm air cap may start at 20 to 100 feet or more above the ground and block the cooler air below it, preventing vertical air movement. Over a wide area, it may be possible to identify the presence of an inversion condition by checking with the National Weather Service. In some areas, during certain times of the year, temperature inversions occur regularly. One method for detecting a temperature inversion in a localized area is to observe a column of smoke rising into the air. Sometimes dust from agricultural operations may serve the same purpose. If the rising smoke column or dust cloud flattens and begins moving sideways or collects in one area above the ground, an inversion condition probably exists. Do not make applications during an inversion condition because the inversion layer traps fine spray droplets and pesticide vapors. These become concentrated, similar to smoke particles in the smoke column. Rather than dispersing somewhat evenly throughout the atmosphere over a relatively large area, the pesticide often moves as a concentrated cloud away from the treatment site. Afterwards, the concentrated pesticide cloud will return to the ground and may cause problems for people, non-treated crops, and other living organisms. An inversion condition can occur when the air is calm with very little air mixing. This condition makes it possible for the cloud of spray droplets or vapor to move slowly downwind. Temperature inversions generally begin before sunset and remain into the early morning or near bodies of water. Minimizing off-target drift. Drift research shows that nozzles and other spray components can produce large spray droplets that have less of a tendency to drift. However, when improperly used, wind shear effects on nozzles result in drift-prone, smaller droplets. Appropriate airspeed and proper nozzle orientation are the two factors that reduce wind shear effects. You need to find a balance between the aircraft's minimum airspeed needed for covering the desired acreage in a given period and the maximum airspeed before wind shear impacts the size of spray droplets. In addition to selecting proper nozzles and finding the balance between proper airspeed to minimize atomization of large droplets, the other challenge you face is to find a balance between drift reduction provided by large droplets and good coverage associated with smaller droplets. Research conducted by pesticide manufacturers, the pesticide application industry, universities, and state and federal regulatory agencies demonstrate that you can minimize off-target pesticide drift during any application operation by selecting nozzle types with orifice sizes that produce large droplets. Wider spray angles typically produce finer sprays. Using a nozzle orientation straight back in relation to the aircraft's level flight line so that the discharged spray is least affected by wind shear across the nozzle face, therefore maintaining the rated desired droplet size. Some research is showing that a single angle of about 5 degrees allows the spray to be directed downward without affecting droplet size. Confining boom length to no more than 75% of the wingspan of a fixed-wing aircraft or the rotor diameter on rotary wing aircraft to reduce drift caused by wingtip and rotor vortices. Increasing system pressure when flying at faster speeds to reduce the amount of smaller droplets. Making sure the positive shutoff and suck-back systems are working properly. Accurately calibrating application equipment, including using a system pressure that is appropriate to the airspeed of the aircraft for maintaining a droplet size that results in optimal spray coverage. Spray droplets are normally finer at greater flight speeds, especially when using wide-angle, fan nozzles, or a nozzle orientation that is not straight back in relation to the level flight of the aircraft. However, for applications using straight stream or narrow angle, 20 to 40 degrees, flat fan nozzles pointed backward, increasing the spray pressure can actually result in a coarser spray if the exit velocity from the nozzle becomes closer to the speed of the aircraft. Doing this reduces the air shear effect. Application techniques. Some application techniques for reducing off-target pesticide drift during an aerial application include leaving untreated buffer zones, 1, 2, or more swath passes wide within the treated site or field, along the downwind edges so that any pesticide that drifts will stay on the treated site. Treat these buffer zones later when the wind direction reverses into the field. Getting good field-in coverage on initial spray runs, in-passes made to fields that are bordered by trees or other obstacles, usually means flying higher, which increases the chance of drift. Flying at the optimum airspeed that will, when combined with pump output pressure, help to maintain larger droplets. Keeping application height between 8 and 12 feet above the target crop. Avoiding applications during weather conditions that promote off-target drift, such as high winds or inversion conditions. Smoke generators. Smoke generators are used on the aircraft to visualize air movement at the application site. You can also use it to identify inversion conditions below the application height. The smoke generator injects oil into the aircraft's exhaust system, which burns to produce smoke. You can control the oil injector with a switch inside the cockpit. When you activate the smoke generator, you can watch the smoke movement to estimate the offside movement potential for spray you are applying. Although of limited effectiveness, you can also use the smoke to locate the position of the previous pass to estimate where to begin the next pass. However, due to possible movement of the smoke and air currents, less reliable for swath marking. Smoke generators are a common part of the onboard equipment found on most agricultural aircraft. One reason for this is that GPS systems have eliminated the need for human flaggers at the application site to position the aircraft for each swath. However, a flagger can typically provide you with information about wind speed and direction. Since off-target pesticide drift is a major concern during aerial applications, a smoke generator provides a better visual picture of wind direction and relative wind speed at the time of spray release. Using a smoke generator before beginning the first pass of an application allows you to make immediate local wind condition evaluations without depending on someone on the ground. Accurate metering and application of pesticides are the key purpose of all aircraft dispersal systems. Dispersal equipment has to deliver the labeled rate of a liquid or dry pesticide formulation uniformly and accurately. Pesticide materials in the dispersal system add considerable weight, requiring aircraft that can safely lift, transport, and make applications when fully loaded. Fixed-wing aircraft used for pesticide application are fast, maneuverable, and carry heavier loads than rotary wing craft. A limitation of a fixed-wing aircraft is the need for a designated landing area, which may not always be close to the application site. Dispersal system requirements. The main function of a dispersal system is to allow you to apply an accurate and uniform amount of pesticide material over the application site as efficiently as possible. Liquid dispersal systems include a pump, a tanker hopper, hoses and/or metal lines, control valves with suck-back features, a pressure gauge, filters, one or more booms and nozzles. Pumps in these systems may be electric or hydraulic motor powered, wind driven, or directly powered from the aircraft engine. Equipment and component factors. Consider several factors for dispersal equipment and components used for aerial application of pesticides. Corrosion resistant. Many pesticide materials are corrosive, so only use corrosion resistant components in the dispersal system. Stainless steel, fiberglass, polyethylene, and polypropylene are non-corrosive, while steel, iron, and aluminum will corrode. In addition, acidic liquids may react with steel or iron to produce highly explosive hydrogen gas. Even though application components are corrosion resistant, the rest of the aircraft may not be, so regularly clean, inspect, maintain, and protect these parts. Leak-proof. Make sure all components of the aircraft's pesticide dispersal system can resist leaks during the rigors of takeoffs, landings, and flight. This includes tanks, pumps, agitators, bearings and seals, hoses, and hose fittings. The presence of pesticide residues on the belly of the aircraft could be an indicator of a leaking hose or connection somewhere in the system. Leaks endanger you and can damage parts of the aircraft. In addition, leaks can expose workers to pesticide materials, contaminate places and objects used by people, and render runways, hangars, and other areas unusable until decontaminated. Leaks may also cause damage to crops and other plantings outside of the treatment area. Make accurate volume measurements. The dispersal equipment has to include a way to measure accurate volume of pesticide materials in order for you to apply the correct amount to the treated area. Be able to produce uniform flow volumes. The dispersal system should provide a uniform flow of the pesticide through the nozzles for even distribution of liquid sprays over treatment areas. Systems that adjust the flow volume according to the application airspeed, referred to as flow control, provide the greatest application volume uniformity, but can affect droplet size. Important qualities of liquid dispersal systems include being dependable and durable, as well as being uncomplicated to service and repair. Spray pumps. The spray pump maintains the pressure in the system to ensure a uniform flow volume and proper atomization by the nozzles. The pump also may power the tank agitation system that keeps the pesticide mixture in suspension. On fixed-wing aircraft, the most common power source for the pump is a fan mounted under the aircraft below the tank. The aircraft's propeller slipstream drives this fan. Some fan-driven pumps have variable pitch blades, so you can change the pump speed and thus output for different application requirements. Ultra-low volume ULV applications may require modifications to the pumping system to make it suitable for such low output. Other types of power sources for aircraft spray pumps include aircraft's hydraulic system or an electric motor that drives the pump. Pumps need enough power and capacity to meet the system's nozzle pressure, flow volume, and tank agitation requirements. The pump needs some extra capacity to make up for pressure loss due to friction in the lines and to operate nozzle anti-drip check valves. If you use a pump with too little capacity, you need to reduce the swath width to get adequate, uniform coverage. However, this wastes time and fuel. The centrifugal pumps, commonly used on aircraft, produce high volumes of spray material, up to 200 gallons per minute or more, depending on the size of the pump. At low pressure, usually ranging between 10 and 70 pounds per square inch psi, centrifugal pumps made from aluminum with bronze or steel internal parts are most common. Centrifugal pumps have a high range of applications, including spraying abrasive wettable powders and flowable formulations, because there is no close contact between moving parts. These pumps usually require operating speeds between 1,000 and 5,000 revolutions per minute RPM. Pressure gauges. Use a pressure gauge as another tool to monitor the spraying system. A pressure gauge helps you determine the correct pump speed or spray valve opening in order to achieve the proper nozzle output, droplet size, and spray pattern. You can use the pressure gauge to monitor and maintain system pressure during application should the electronic flow control system in the aircraft stop working. A pressure change in the system during spraying indicates potential problems. For instance, clogged nozzles or filter screens could increase pressure. A drop in pressure might indicate a broken nozzle, a disconnected line, another type of leak, or pump malfunction. When a pressure change occurs, inspect the system to determine the cause and make necessary repairs. To assure precise readings of pressure at the nozzles, connect the pressure gauge sensor line to the spray boom. The pressure gauge in the aircraft needs periodic checking. When connected to the same pressure source, compare readings from the aircraft's gauge to another gauge known to be accurate. Inspect and frequently clean check valves to assure they work properly and are not leaking. Replace diaphragms when they show wear. You can flush needle and seat types of anti-drip check valves without disassembling the nozzle by pulling on the needle, which typically clears the valve of debris and stops leaks. Aerial application considerations to reduce drift and off-target applications. Aerial applicators have all the challenges of managing pesticide drift as other applicators do, but they also deal with a release, boom, height of anywhere between 8 and 12 feet. This gives the effects of wind and carrier evaporation additional time to affect the droplet. Aerial applicators may need to adjust droplet size as the temperature, humidity, and wind change throughout the day. Every plane must be set up individually. Even similar planes may require very different setups to provide optimum patterns. To reduce the probability of smaller droplets being caught up in the wing vortices, general recommendations for fixed-wing aircraft suggest that boom width not exceed 75% of wingspan. Boom widths of 60 to 70% may be necessary on some planes to minimize the effect of vortices. Rotary wing aircraft can also have a vortex effect, and boom widths should be restricted to no more than 80% of the rotor width. Just as a heavily loaded boat moves more water, a fully loaded plane displaces more air, increasing the vortex effect. Use caution when spraying with a full load near sensitive areas. Reduce turbulence. Whenever possible, reduce the amount of turbulence in the area where the droplets are released. This may be done, for example, by dropping the boom below the trailing edge of the wing, moving or shielding obstacles such as flow monitors and piping, and using nozzle drop tubes under the fuselage. Also, look for bent boom hangers or blunt surfaces that may cause air turbulence. Adjust height. Application height also depends upon the plane, but is usually from 8 to 12 feet. Generally, smaller planes fly lower, and larger planes should stay higher. Heights that are too high increase the opportunity for wind and evaporation to affect the droplet. Flying too low may push the pattern outward due to ground effect and increase drift potential. Adjust speed. An airspeed that is too fast can cause increased wind shear and produce driftable fine droplets. An airspeed that is too low results in tail dragging that can increase turbulence and drift. Adjust nozzles. Closely follow the nozzle manufacturer's recommendations for setting up nozzles. To reduce fine droplets, nozzles generally should be pointed parallel with the airflow. Be sure that the nozzles are parallel in flight and not while sitting on the runway. Use the bottom of the wing to gauge airflow. Many things to consider. Many factors can influence drift during aerial application. Consider all the following, adjust where possible, and wait for appropriate conditions. Please review the chart on the screen for static factors, adjustments where possible that can be made, and waiting for the appropriate conditions. We'll give you a few moments to review this. Making a pesticide application. The reasons for following proper aerial pesticide application methods are to make precise, safe, and legal aerial applications consistently and to minimize the off-target movement of pesticide droplets. Proper application methods include knowing how to recognize the factors and conditions that contribute to off-target pesticide drift and other off-site movement, and know how to minimize off-target pesticide drift and other off-site movement. Inspect the application site and surrounding areas for hazards before beginning the application. Watch for hazards throughout the application operation. Fly an effective application pattern and make safe and efficient turns and passes. Recognize the atmospheric factors that influence the stability and maneuverability of the aircraft. Use DGPS or other guidance systems. Agricultural aircraft are highly visible and noisy, and as a result, some people view aerial pesticide applications as nuisances or hazards. The sight of an aircraft flying low over fields is serious and sometimes anxiety-producing concern for some. When you make aerial applications, be aware of these concerns and, when necessary, be sure to acknowledge them by taking steps to foster better communication with the public. Notify people in the area about a planned application and make efforts to migrate noise in areas where people live and work during varying or application operations. Checking the application site. Upon arrival at an application site, fly an initial inspection pass to verify that local weather conditions are suitable for the prescribed aerial application work. Agricultural workers, spectators, trespassers, and others, including their vehicles and equipment, are not within or immediately adjacent to the application area, especially downwind of the site. Livestock are not in the application area or adjacent areas where they may come into contact with the spray. Checking the application site. Crops adjacent to the application site match those identified on the work order. If in doubt, verify the type of crop with the grower before beginning an application. All members of the ground crew assigned to this operation are present and ready to begin their duties. The communication between you, the ground crew, and the base location is functioning correctly, and that you have a working backup communication plan in case of equipment failure. New technologies. Electrostatic spray technology in aerial applications is a method that enhances the efficiency and precision of pesticide application. Here's how it works. Charging mechanism. The technology uses induction, corona, or contact charging methods to charge the droplets. Electric field. Charged droplets are then directed by a high voltage, static electricity field, causing them to rapidly deposit along the electrical field lines in the air. Targeted deposition. This results in a more uniform coverage of the target area and reduces drift as the droplets are attracted to the target surfaces due to their charge. Environmental benefits. It allows for lower chemical application rates, achieving disease and pest control while reducing environmental pollution. This technology is particularly promising when integrated with unmanned aerial vehicles, UAVs, as it can potentially increase the deposition of droplets on the target and further minimize environmental impact. However, there are still challenges to be addressed, such as optimizing the test technology for charged droplets and understanding the impact of UAV rotor wind fields on the spraying process. Overall, electrostatic spray technology represents a significant advancement in aerial pesticide application, offering a more efficient and environmentally friendly alternative to traditional methods. Final tidbits. Avoid spray drift impacting non-target sites by taking the following. When treating next to sensitive areas, spray in the morning when up canyon and upslope winds are well established and blowing up canyon. Most sensitive areas are down canyon. The specific time will need to be determined by real-time weather monitoring. Maintain boom pressure at less than 40 psi. Monitor spray pressure during flight, since changes in pressure can change the application rates and may change the droplet size. Check nozzles and review calibration with pilot. Begin the first swath 300 feet from any sensitive area. Mark boundaries so they are clearly understood by the pilot. Fly area with pilot prior to treatment to verify location. Use GPS to document boundaries and record treatment flight paths. Monitor treatment boundaries next to sensitive areas with spray deposit cards to detect any possible drift. Train people on how to handle the cards, interpret the cards. Many things can contaminate the cards, such as dew, moisture from hands, insects, and also document results. Card lines should also be placed in the treated areas under full spray to serve as a reference. Monitor and record weather in the area. The weather should be monitored in real time for operational control and to help with the post-spray analysis. Strive for winds from 3 to 6 miles per hour or per label instruction. Do not treat if rain is predicted within next 24 hours. Consider using Forest Service, Kramer, Barry, Grimm, FSCBG, or AGDISP computer models to evaluate drift potential and to develop operational and drift protection measures prior to treatment. Congratulations, you have completed the course. Please continue to the quiz. Please send us your thoughts on the course. We would appreciate the feedback. pestceus@gmail.com.